Okay, welcome everybody. Today I'm going to talk about brains on the edge. So I will show a real-world example where we implemented an edge workload with GPUs. And yeah, in the beginning I will show some theory and go into the deeper into it, why AI matters now, and then I will come to some examples, and then I will show the architecture of a real-world scenario. First of all, maybe some information about me. I'm the domain lead for cloud transformation data infrastructure at Betelligent, and I'm also the community lead for IoT and industrial IoT. That's maybe the reason why some slides maybe a bit industrial focused, but yeah, this is also in the end an industrial use case which I brought with me. Yeah, so maybe let's start with the edge computing. So what means edge computing? As maybe everybody already knows, edge computing means that we will bring the compute power closer to the devices, to the IoT devices in the field. We can have several layers in an edge architecture. I have here one example which we often use. So we have the three layers where we have the near edge, the far edge, and the device edge, where we can then bring our different data services. So for the services which are drawn here are examples which we used for this use case, which I will show in a few minutes, and also which are used within the industrial use cases a lot. Not every layer from this example here is required for the edge use cases with AI. It depends on the architecture and also on the use case from the client. So sometimes there is a central cloud infrastructure and then only one device, IoT device infrastructure, for example, where we have an edge device and connect it and deploy our ML models. But sometimes, for example, for the factory use cases, we have an overall factory edge device or some line edge devices, and then some smaller devices closer, edge devices closer to the machine, where we also want to collect the data and where we want to process and predict the values there. So this for the start. Then maybe let's see why AI on the edge matters now. So here are some points about why AI on the edge matters now. It is often we have the requirement that we really need to do decisions in real time or near real time. So therefore we would need to have low latencies, and we would need to bring our models, which we maybe have trained in the cloud or also in some on-premise data centers, then closer to the devices to make the predictions there. For example, if we have some image classification where we need to check the quality of a certain product or something like this, then we want to directly send an action so that we can go farther with some decisions. Then we have often we get some depends on the client, but we get often some privacy and security requirements where the company says, okay, I have some data which cannot go into the cloud. I have other data which can go into the cloud, and there we really need to have the infrastructure also on premise, where we can not only predict or inference our models, also train the models, and then use them in the field. We have the the enhanced data economy. So I think in the last years there was a huge movement into the cloud, but as I think we can see now is also that this movement is going back, because many companies see okay, we moved everything into the cloud, but now we have some servers in our on-premise, for example, which are not used, and so on. So how can we use these services, these servers, and maybe reduce cost with it, and also to it will maybe also help the footprint to not only use the cloud data centers and servers, also some we can see in the news that also the cloud providers are still getting more and more issues to create new data centers and so on. So therefore, the hybrid architecture is a common architecture nowadays. Then the reliability and offline capability. So often devices are not connected to the internet the whole time, so we need to enable them to do also predictions when they are offline, or to keep the devices working and store the data, keep the data flowing when the devices are offline. And then at the last point is scalability. With scalability, it means not the scalability within the cloud, but it means the distributed scalability closer to the devices, or where the data is getting created. So, and what makes it possible today? I think one important point is that we have more and more efficient ML runtimes. So we have lightweight ML runtimes like TensorFlow Lite or OpenVINO, which we can use to then use them for model inferencing, or also model training on the edge devices. We have nowadays stronger hardware, so there's many hardware, GPU hardware, which we can use, which also brings some complexity into how we can really use them efficiently with Kubernetes and so on. But we have the possibilities now to use edge computing or use edge devices for ML model inference. Then we have the Kubernetes, which is still evolving for the edge. So we have the different kinds of Kubernetes. We have k3s, we have k0s, which we can use on the edge and is a lightweight Kubernetes. And then we have also the smaller and smarter models, which are optimized for edge computing. And last but not least, also the cloud native toolchains, as we saw it in the first architecture slide, with, for example, GitOps toolings to deploy or to bring our infrastructure on a scalable way into our edge devices. We can scale really fast with several of devices which we use. But we still have challenges with edge and edge AI inference. So we still have some resource constraints. So sometimes the servers or the environments we have on-premise are limited, and we really need to therefore really need to check what we really want to deploy on the edge, what we really can also deploy on the edge, and what we should maybe better take into another place to keep these constraints. We have the topic of system resilience. Often we have also with the use case I brought with me, we have there some. The devices are not every time reachable. So if there's something if they break something, maybe there's no internet connectivity, maybe there's nobody close to the hardware who can support and check what are the issues. So these are challenges we see quite often. And then also the operational complexity. So it is also hard to manage all these applications across the different hardware we have within the factories. Also maybe within the devices where we want to do the model inferencing, and then for the whole part, the skill gap is also one hard challenge, because I think with bringing the compute power, or bringing the data engineering closer to the devices, we also have new people which are getting involved and which need to be skilled up, and this is also one hard challenge within the edge AI inference, because we do not have everywhere the technicians or the cloud or the edge engineers, or also the data scientists, which can then manage all these models and help. What is the first part, how we tackle this? This is, I think, an already known pattern, which we also use for our ML model, edge AI, and model inferencing when we use it on the edge. So we try to make the whole process modular, so that we can then have the different layers for feature, training, and inference in separate models to use them and scale them up, and bring maybe some parts stay in the cloud in a central place, and other parts we bring it closer to the devices and use there the model inferencing. Yeah, we have, for example, here we see we have some data stores also with the historical data, where we can create then the features out of it. We have the feature store, where the features then are getting stored into, and then we use them for training, and also for training, and also for inferencing, and put the model into the model registry, where we can then pull it from the registry as soon as we have internet into the different edge environments and the devices. So here is an overview of some real-world examples we already saw. So we have, for example, the autonomous vehicle perception, where we there have self-driving cars, for example, where we need to deploy our AI models into the edge devices there. We have the edge-based security use cases, where we use there the camera systems to see if people are in dangerous environments, and to then maybe stop the machine and so on, and also to see if the people are wearing their security clothes and so on. So this is a really common use case. We have the agriculture via drones, where we can this is something from a small startup, where the startup has drones which checks the different agriculture fields outside, and where then can be done real world or real-time decisions on what to do, and there's no real network needed. And then the last one, which also will be the use case which I brought with me, is industrial predictive maintenance. So there we have, for example, some devices which are or some gear where's gear on different devices which are maybe not every time connected to the internet, and where we need to predict failures, and also to enable direct actions to within the in this use case. Maybe it gets a bit clearer with the example here. So we had a customer which came to us and said, we produce gear for ships, and we would like to have there a predictive maintenance model so that the model can still run when the ships are on the sea and do not have connectivity to the internet, and to predict, okay, when the ship maybe has to go back into the harbor, and because of some if something breaks, and also and to predict maybe when we can so the percentage of lifetime of the gear, so to see if we need to maybe change the gear also in front of the or before the ship starts into the sea, to then help there to not break in a bad location, I would say. What we used for the use case, so we used there the stackable data platform within an Azure environment, so in Azure Kubernetes. The whole platform was then deployed or built on top of Kubernetes, so that the client, this was also one requirement, the client wanted to be flexible with the cloud infrastructure as well, to maybe then in the future go to another cloud provider, and therefore we used a Kubernetes-based approach to with the stackable data platform to have there the flexibility. And then we used the TensorFlow and TensorFlow Lite model training and inference, so that we have a light model which we can deploy on the edge into the edge devices on the ships. So directly in the beginning, we had some prerequisites which we need to address. So first of all, what we learned also is it is not for every hardware. So therefore, so I mean, if you use plain k3s, you can use it with mostly every hardware. But the customer also was thinking about how we can use maybe managed Kubernetes on the edge. There are also some possibilities with Azure, but there it is really required that not every hardware is compatible with the managed Kubernetes. There it is necessary to check if there are possibilities. Also, there was one point with some Linux distributions where you can also see it on the NVIDIA pages, where you can see, okay, some Linux distributions are supported, some others not. So this is really these are really hard requirements which need to be fulfilled. And then also on the container runtimes. So for our use case, or if you use k3s, you have the container runtime. So there are no issues, but the container runtimes are only these three supported, but the Docker runtime is also deprecated. And then for software and drivers, so it is necessary to install we used in the use case the NVIDIA GPU, so therefore it is really necessary to install the different GPU drivers, the container toolkit, and also the Kubernetes device plugins for getting the GPU also allocated from the k3s. Then let's have a look into the high-level architecture. Here we can see how we set it up on the hybrid cloud environment. So we had, for example, on the this is all on the edge and on the ship actually. So there we have our k3s Kubernetes deployment. There we have an MQTT broker which gets the live telemetry data, pushes it into the Kafka, and there we also have the possibility on the edge to give these the people on the ship some dashboards and to see and check how is the current state of my gear I'm using within the ship. There we used in the cloud and also on-premise Superset to have the dashboards developed via central reporting engineers. They could then develop new dashboards as well, and we could then use them in the edge environment too. And within the cloud, we have the lake-based storage with the Azure Blob Storage. There we can use Spark and Trino, which is coming with the stackable data platform natively to build data processing, and this we can also use then to train models with TensorFlow and also to register the models into MLflow. And when the ship is in the harbor and connected to the internet, then we have actually 3 things we will then sync. We will first of all get the new model if there was a new model version uploaded and so on. We will get the new model into the edge device. And also we will sync the data which we collected during the way on the sea. We will bring the data then into the Azure cloud to use this for model retraining or other use cases in the future as well. And for the real-time predictions, we use the TensorFlow IO for Kafka to then on the sea do the real-time predictions and see what is the current lifetime of the gear. I think so. I'm not the data scientist who trained and did the whole model stuff, but I know that there was one big issue they had because. Within ships, the gears are quite big and robust, and it was really hard to get the failures out of it because there are mostly no failures, and this was one big issue on how to train the model on the correct way. The customer was also, it is hard to maybe simulate or break one gear just to get some failure points. That is what the data scientists brought with me. But this was one big issue there. And then maybe the last slide. So what were the key takeaways of the use case? The key takeaway is the GPU integration with K3s. This needs to be set up in front, as it was showed on the other slide. It is not natively included, but it is possible with K3s. You can implement or use. For example, here we did it with the NVIDIA. You can use the NVIDIA GPUs. And to train and also to inference models on the edge. It is really necessary to check if it is compatible in the beginning of the project. So some customers are. I think often they think it's we have a GPU, so just start. It has to work, but it's not with everything possible. So there, be aware that maybe also the client has to maybe need to buy a new hardware or also change their idea or their what they wanted to do. What we saw there as an outcome of the project was that we, with this solution, it was possible to reduce operational risk. It is still not running that many years, and as I already said, it is the gear is not breaking. I mean, I think in 20 or 30 years there was one break, but if it's a break on the sea, then it's it's really bad. So that is why they wanted to enable it. And then we have the resilient and autonomous operation, which is also something where we, for the hybrid architecture, we did the model training here on a central place, but the possibility is there that also if the ship is maybe many time on the sea, then that they can also do model retraining or something like this on the ship infrastructure. Okay, that was it. Are there any questions?
Hi, thanks for the talk. I have a question regarding the GPU configuration. Did you use the NVIDIA GPU operator, or did you directly configure first Docker and then only change the pod spec to use another engine for that?
We used directly the NVIDIA operator, and we installed it with the NVIDIA operator, and that was quite easy. We have with the k3s, we had also the container registry, so this was container runtime, so this was there quite easy.
You also mentioned k0s as distribution. What is the main difference between k3s and k0s, and why did you prefer k3s?
So we did here prefer k3s because it was k0s is it is more lightweight than k3s, as I understood, and also we used it here because the k3s we used it here because that was the container or the Kubernetes distribution which was there when we implemented this use case, commonly used, and where we had the most experience. So it was not a decision against k0s. I think if we now would do the same use case, we would need to evaluate, but the k0s, I think, there, because in the ships we do not have this small edge devices as it is maybe on other IoT use cases. So there it was with k3s, everything fine possible.
Well, I guess what you just said leads to my question. Did you have any power requirements, or how much power could you use for this entire project? Because we work with edge devices that take about 5 watts.
So on on the use case we have these ships. So these are really huge ships. So we had there actually not really the power constraints. Where there are more constraints is if you work with drones. If you maybe there have in this use case, then AI devices or really want to use some GPU possibilities, that makes it even harder. But within the ships, we did not have had power constraints. Yeah.
I have a question. How were you able to determine if you saved cost? Because you said only in 15 years only one gear actually did break. How can you validate if you're actually saving costs or if it's like a nice feature?
That's correct. So this is one thing which the client actually predicted. So this is because we cannot see if there are really gears failing, maybe, or we can predict it in certainly in the next 5 years that one gear maybe which is working already 30 years that it will break. But this is something which we can really prove in the next couple of years. But the client, this was at least that was what the client predicted, and the data science department there communicated to the management. So this was something which I took with me. But until now, there was we have still no break within the gear. So this is really something that's good question because it's hard to predict this.
Last question.
Just one question around deploying on the edge. Have you had scenarios where you're looking at trying to deploy in an edge compute situation where the form factor of K3 is just too much to handle the edge use case, where really you just don't have the memory or the capacities to do what you want with the overhead of K3? Or in most cases, have you been successful in seeing K3 as a viable means to be able to handle your edge compute scenarios?
So in the current use cases we are implementing, so mostly in manufacturing use cases or such use cases, as I explained, K3s was sufficient. But I think if there are other use cases, then maybe it is necessary to think about K0s maybe or something like this, because it's for me there's Kubernetes is the distribution itself is the best case, because I really can use the GitOps tools and everything to deploy it in a fast way. So therefore I would then check if I cannot do it with K3s. If not, then I would need to check if we can do it with K0s or something like this.